Welcome. In this video, we are in Chapter 5, and we look at Section B, Equivalent Fractions. We will look at the fraction wall or length model for equivalent fractions, the area model, and we'll look at fractions given numerically. How do I tell if two fractions are equivalent if they are given numerically? We begin with the fraction wall or the length model. The idea is that the length of this thing equals 1. So from the far left all the way across to the far right, that has a length of 1. So it's divided up into blocks or bars that have various fractional lengths. So on the top row, we see that each of those blocks has a length of 1/2. And below that, each of those blocks has a length of 1/3. These are all unit fractions that are put together to make a total length of 1 going across. So I can identify some equivalent fractions by using this kind of picture. For example, let's identify fractions that are equivalent to 3/4. So how do I find 3/4 in this picture? Well, 3/4 is literally 3/4. So I have a fourth, a fourth, a fourth, and that brings me to this point here. So working from the left, I put my 3/4 together and I get that. Looking down, I see a couple other breakpoints between blocks, and now I can figure out some other equivalent fractions. Oh, it looks like I have a certain number of eighths there. In fact, that's 6/8. So 6/8 is equivalent to 3/4. Or I can look at my twelfths. I have a certain number of twelfths there. In fact, I have 9/12, so 9/12 is also equivalent to 3/4. How about the fraction 2/3? Let me erase the ink. I'll give you a couple seconds. What are some other fractions equivalent to 2/3 looking at this picture? First, I identify 2/3 in the picture. So it looks like I have 1/3 and 1/3. That gives me 2/3. Looking straight down, I see a couple other breakpoints. A certain number of sixths. So in fact, that looks like 4/6. So 4/6 is equivalent to 2/3. And a certain number of twelfths. How many twelfths is that? That looks like 8/12. So there we go. So we can use the length model or this fraction wall model to help us figure out equivalent fractions. Another common way is looking at areas, or pie diagrams really. Equal shaded areas are equivalent to the same fractional part. So in the picture on the left, 2 parts out of 5 are shaded. So the shaded part represents the fraction 2/5. And you can see that the same area is shaded on the right, it's just divided up differently. There's 4 parts that are shaded there, and what's the total number of parts altogether? It's 10 parts. So I have 2/5 is equal to 4/10. These are equivalent fractions. They equal the same thing. On the right, actually it looks like half the area is shaded, so I can just write down 1/2. But I might think about it as, well, on the right, 3 out of 6. And in the picture on the left, well, it looks like maybe 6 parts are shaded, 6 parts out of, and if you do some careful counting, 6 parts out of 12. So 6/12 and 3/6 are equivalent fractions. Here's one more along those lines. It's a little bit different though. In this case, let's see, on the left I have 1, 2, 3, 4, 5, 6. 6 parts out of 9 that are shaded, and on the right it looks like 4 parts out of 6. So 6/9 is equivalent to 4/6. Why is this different? Well, let me go back a slide and look at the previous pictures. Previously, if I look at the picture on the left, I have those 2/5. Each of those segments that make up 1/5, that segment was divided nicely into 2 parts in order to get my equivalent fraction. And something similar was going on with the 3/6. If I take one little pie wedge representing one of those parts, that one pie wedge was divided nicely into 2 parts. But in this new problem, we don't quite get that. If I take one pie wedge, it's not really represented nicely in the picture on the left. In fact, the only way it really works is if I take 2 pie wedges on the right, and that corresponds to 3 pie wedges on the left. So things don't break up quite as nicely in this picture. But the overall point that I really want to make is, remember, these are equal shaded areas. So any way that I divide them up, as long as I'm dividing into equal parts, it will produce equivalent fractions. Let's tackle fractions that are given numerically, because we can't always just rely on pictures. We need our intuition to evolve from understanding pictures to understanding the more abstract representations of fractions. How do you know? 2/3, 4/6, are these equal? In other words, are these equivalent fractions? Let's approach it with the two models right away. How do I think about this? Well, 2/3 with the bar model, I divide it into 3 equal parts. I shade 2 of them, and if I compare that with sixths, well, what am I doing with sixths? I'm taking each third and dividing that into 2, and I see, oh yeah, if I shade 4 of those sixths, I get the same thing, and so I'm convinced. Yes, those are 2 equal fractions. Or we could do something similar with the area model. I can divide into thirds, I can divide into sixths, and then shading 2/3 is the same as shading 4/6. But let's move away from this and think abstractly, more symbolically. How do we know? Because if I want to test 18/27ths and 10/15ths, I need to find some other way other than drawing pictures. All right, so I propose 2 ways that we think about understanding how to determine if 2 fractions are equivalent or not. The first is a little simpler. It doesn't always work, but here's the idea. Multiplying or dividing the numerator and denominator by the same number produces an equivalent fraction. For example, find some fractions equivalent to 3/4. Well, if I multiply the top and the bottom by 2, I get 6/8. If I multiply the top and the bottom by 3, I get 9/12. If I multiply the numerator and denominator by 4, I get 12/16. And we can use the pictures to reason out why this is reasonable. If I start with a picture for 3/4, and then I take all of those segments, and I take each segment and divide it into 2 parts, I'll find that shading 3/4 on top is equivalent to shading 6/8 on the bottom. It's just like I've taken each part on the top and divided that into 2. So going from 3/4 to 6/8 is like taking every segment in a 3/4 picture and dividing it into 2 parts. And similar with the 9/12, I would take every segment and divide into 3 parts, or the 12/16, I would take every segment and divide into 4 parts. Now, the reverse process also works. So then I should be able to take something like 24/36 and realize, oh, well, maybe I can divide the numerator by 2 and get 12, and divide the denominator by 2 and get 18. So there's an equivalent fraction if I divide both the top and the bottom by 2. Or I can divide both the top and the bottom by 3, in which case I get 8/12. And what is the most that I can divide out? In fact, 24 and 36 have a common factor of 12. So if I divide out that greatest common factor, I get 2/3. And this is what we do when we reduce fractions. That's when we're dividing the numerator and denominator by the greatest common factor. And we produce an equivalent fraction. More generally, here is the sophisticated way to determine when 2 fractions are equal. One fraction is a over b, the other fraction is c over d, and these 2 fractions are equal when a times d equals b times c. For example, are 4/10 and 10/25 equivalent? The first thing I might want to do is say, well, is one just a straightforward multiple of the other? But 10 to 25, it's not so easy to work out maybe. But if I do cross multiplying, there's my a and d, 4 times 25, and here's my b and c, 10 times 10. Are those equal? 100, 100, yes. So these 2 fractions are equivalent. How about on the right? So in this case, my a and d are 7 and 3, 7 times 3. The b and c are 11 and 2, so 11 times 2. And now I compare 21 with 22, and they're close, but they are not equal. So these are not equivalent fractions there. This kind of process can be used to figure out a missing number in a fraction. What number should I put above the 12 in order to make these two fractions equivalent? Well, let's do a little algebra. I'll call this x, cross multiply, and I get 15 times x, and cross multiply the 12 and the 10, so 12 times 10 is 120. And at this point, you can divide both sides by 15 and use your calculator to find an answer. Or maybe you notice that they are divisible by 5. Each side is divisible by 5. So you could start by dividing both sides by 5 and say 3x equals 24. And then, and then at this point, maybe you divide both sides by 3 and you end up with x equals 8. Now, something that will make your work a little bit easier with this kind of calculation is if one of the fractions can be reduced, just go ahead and reduce, because after all, 10/15 can be reduced fully. The numerator and denominator each have a factor of 5, and that becomes 2/3. So now when I cross multiply, I get 3 times x equals 2 times 12. And that just takes me directly to the second equation I had before, which is a little bit easier to solve. Divide by 3, I get x equals 8. So here we go. We figured out our solution. 8/12 is equivalent to 10/15. All right, that's a good place to stop. We've looked at equivalent fractions from a length point of view, from an area point of view, and then finally from a numerical point of view.